Picture this. You're standing on the deck of a ship, just staring out at the endless ocean stretching all the way to the horizon. It looks incredibly calm, right? Just this vast, still expanse of blue. But what if I told you that back in 1992, a cargo ship accidentally spilled thousands of rubber toys into the middle of the Pacific Ocean, and years later, those exact same toys started washing up on shores all over the globe? I mean, some even made it all the way to the North Atlantic. So how on earth did they get there? It wasn't boat engines, and it certainly wasn't wind.
It was exactly 28,000 rubber ducks and other bath toys. Oceanographers actually ended up tracking these 28,000 toys, affectionately nicknamed the Friendly Floaties, for years. Some drifted across the Pacific, some ventured up into the freezing Arctic, and others eventually hit the Atlantic. What this massive, totally accidental science experiment proved is that the world's oceans are absolutely not isolated puddles. They act as this massive, interconnected global highway system, moving relentlessly right beneath the surface.
Welcome to This Explainer. Today, we are diving deep into the grand, invisible, and frankly, incredibly powerful forces of ocean circulation. We're not just talking about water sloshing around here. We're looking at the hidden highways of the sea, forces that have guided intrepid early explorers, totally shaped our global climates, and literally connected continents. Here is how we're going to break this all down today. First, we'll look at the ocean's hidden highways. Then, the Atlantic as the explorer's ocean, followed by the Pacific, our dynamic giant. After that, we'll check out the Indian Ocean's monsoon engine, the absolutely unstoppable Southern Ocean, and finally, we'll wrap up with exactly why all of this matters to us today. All right, let's jump right into part one, the ocean's hidden highways. We really need to look at the macro-level engines driving all this water.
So, surface waters don't just wander around aimlessly. They actually organize themselves into 5 major circular systems called gyres. You've got the North and South Atlantic, the North and South Pacific, and the Indian Ocean gyres. These massive systems rotate because of global wind patterns and the Earth's spin. You know, the Coriolis effect. For early sailors, though, these gyres were a massive double-edged sword. Catch the right current and you're flying. But if your ship got caught dead in the center, you were stuck in a windless trap, barely moving at all. Fun fact, those calm centers are exactly where we find those enormous ocean garbage patches today.
But hey, that's just what's happening on the surface. Beneath all that lies the thermohaline circulation, which is basically a giant global ocean conveyor belt. Here's how it works. Warm water travels north up near Greenland, loses its heat, becomes incredibly dense, and just sinks. This deep, freezing cold water then slowly travels southward along the ocean floor all the way down to Antarctica, where it catches powerful currents and spreads out into the Indian and Pacific Oceans. It's an epic journey that can take hundreds, sometimes even thousands of years to complete. And, as the saying goes, what goes down must eventually come up. This deep water rises again through a really cool process called upwelling. When surface winds push topwater away, that deep, cold, nutrient-packed water rises up from the bottom to replace it. This is a huge deal because this upwelling brings life-sustaining nutrients right to the surface, supporting massive fish populations and completing a cycle that redistributes heat and regulates our entire global climate. Honestly, without this conveyor belt, our Earth would be completely unrecognizable.
Moving right along to part 2, the Atlantic, also known as the explorer's ocean.
It is wild to see how these Pacific currents literally shaped human history. Think back to 1492. Christopher Columbus heavily relied on the warm, westward-flowing North Equatorial Current and the trade winds to keep his ships moving steadily toward the Americas. Over in the 15th century, Portuguese sailors developed a technique called the Volta do Mar, using the cold Canary Current to totally revolutionize long-distance navigation. Skip ahead to the 18th century, and you've got Benjamin Franklin actually mapping out the fast, warm Gulf Stream because he realized it was acting like an express lane for ships heading to Europe. And, on a much more tragic note, it was the freezing southward-flowing Labrador Current that dragged dense fog and dead-sea icebergs straight into the shipping lanes, ultimately sinking the Titanic in 1912.
Now, if you head further south in the Atlantic, you run into the Brazil Current flowing warmly southward right into the Falkland Current, which is bringing freezing sub-Antarctic water straight north. When these two meet, oh man, it is a dramatic clash. This confluence creates an unbelievable amount of biological richness. It's easily one of the best fishing regions in the South Atlantic. But because of that clash, it also whips up some incredibly unpredictable, turbulent, and downright dangerous conditions for any sailor brave enough to try and navigate it.
Okay, let's head west to part 3, the Pacific, the dynamic giant.
You might actually already be familiar with one of the Pacific's most famous currents thanks to pop culture. I'm talking about the East Australian Current, or the EAC, from the movie Finding Nemo. You know, where it's shown as this ultra-smooth, fast-moving underwater highway for sea turtles. Well, reality is a bit different. While it definitely is warm and fast, it's also incredibly dynamic and turbulent. It is absolutely packed with swirling eddies and chaotic water masses that can drastically alter a ship's navigation and whip up some really rough seas. Definitely not a smooth, relaxing ride.
Let's look over by Japan, where we see another incredible clash, a lot like the one we just talked about in the Atlantic. So you have the Kuroshio Current, which is this incredibly fast, warm, and highly salty current. Locals often call it the Black Stream because of how dark the water looks. When this current surges north and slams into the freezing, nutrient-rich Oceanography current moving south from the Arctic, they create a massive convergence zone. For marine life, this is a jackpot. It creates one of the most productive fishing grounds in the entire world, just loaded with tuna and salmon. But for humans on ships, this sudden meeting of warm and cold water produces incredibly dense, hazardous fog and wildly unpredictable sea states.
And of course, we absolutely cannot talk about the Pacific without talking about El Niño. Now, the really crucial thing to understand here is that El Niño isn't actually a current itself. It's a climate pattern that suppresses a cold, highly productive upwelling current called the Humboldt Current off the coast of South America. What starts out as a localized nightmare for fishermen in Peru, where the fish literally just vanish, quickly cascades into a massive global weather disruptor. We are talking about changes to global rainfall, severe droughts in some regions, devastating floods in others, and totally shifted storm tracks across the entire planet.
Let's keep moving. Part 4. The Indian Ocean, also known as the monsoon engine.
So the Indian Ocean is incredibly unique because it is entirely ruled by seasonal monsoon winds. During the southwest monsoon, the winds and surface currents, like the super powerful Somali current, flow fiercely to the north. But then, when the northeast monsoon hits, the entire system literally just flips. The current completely reverses direction and starts flowing south. It's wild. Ancient Arab and Indian traders mastered this natural rhythm thousands of years ago. They would sail one way, just hang out and wait for the seasonal flip, and then sail right back. They essentially built the world's very first maritime trade networks, long before modern science even understood why the currents were reversing in the first place.
The Indian Ocean also has a few real rebels in its waters. Take the Agulhas Current near the southern tip of Africa. It's incredibly fast, but when it crashes into opposing winds, it creates these absolutely terrifying, deadly rogue waves that sailors have feared for centuries. And then you have the Lewin Current. Usually, currents on the eastern boundary of an ocean are cold, but the Lewin? It's this bizarre warm current that flows south along Western Australia. It completely defies typical oceanographic rules, bringing tropical marine life way further south to latitudes where they honestly have no business being.
All right, time to zoom back out to the macro level with Part 5, the unstoppable Southern Ocean.
Driven by these relentless, howling westerly winds, famously known as the Roaring 40s and Furious 50s, the Antarctic Circumpolar Current, or the ACC, is an absolute beast. It is, without a doubt, the largest ocean current on Earth. Why? Well, because it's the only current on the planet that completely circles the globe without hitting a single landmass to slow it down. It just flows continuously from west to east, moving more water than all the rivers in the world combined.
And the ACC plays this incredibly fascinating dual role for our planet. On one hand, it acts like a giant icy fortress wall. It's a massive thermal barrier that isolates Antarctica, keeping it locked in a deep freeze. But at the exact same time, it's the ultimate uniter of the world's oceans. Remember that deep Atlantic water we talked about earlier? The ACC grabs that water and distributes it out into the Pacific and Indian Oceans. It is quite literally the beating heart driving the entire global conveyor belt, perfectly balancing heat, nutrients, and salt across the globe.
Which brings us to our final section, Part 6, Why Ocean Currents Matter.
As you've seen in this explainer, these currents are so much more than just a dry scientific concept. From outfitting ancient explorers like Columbus, to dictating modern global shipping routes, to sustaining the delicate marine ecosystems that feed millions of people, these hidden highways dictate the success, failure, and frankly, the survival of life on Earth. Most importantly, they regulate the very climate system that keeps our planet habitable.
I want to leave you with this final thought. The next time you stand on a beach and look out at a perfectly calm, still ocean, remember the massive, invisible, and incredibly powerful forces moving relentlessly right beneath the surface. And as you think about how deeply interconnected all these systems are, ask yourself, how might these vital, life-sustaining currents shift in our rapidly changing climate? And what on earth will that mean for the rest of us living above the surface?